So if you wanted to find an area under a curve from A to B, well, this is problematic if that line is curved, because you don't have a nice formula for it. But you could get pretty close. Like if you did these rectangles on the right and added them up, you'd actually be pretty close, don't you think? Like the first rectangle is an overestimate. The second rectangle is an overestimate. The third one, ooh, going right, that little space that's over and the space that's, it looks pretty close. And then this one's an underestimate, and the last one looks actually quite accurate. And we would get an estimate for the area that might be pretty good, right? And might be pretty good is usually what's used in like science. But mathematicians are particular, right? They're like, oh, might be pretty good, could be better. So they keep trying to do better than last time. And that idea of doing better is if we keep making those rectangles smaller or smaller. Or maybe someone says, I'll do rectangles below, you do rectangles above, and if we take the average, that'll be better. So we have all of these ideas historically happening, and this historically goes back to the Greeks. They were thinking about this problem already. Now, what's going to happen is we're going to find out that this ends up turning into an integral. But how that works and why that works is going to come in time. So, assume we have a constant function. So f of x is just always h. Right? The graph would be a horizontal line. Then the area is really easy because you would just have to figure out what this height is, and then whatever this length is would be perfect. Because it would be a perfect rectangle. So if you had a completely flat line, you would be really good. So here we have 1/2 x plus 3. And if you had to find that area, chances are you could actually do this with the shapes that you know. I'd be like, hey, wait a minute. What happens if I do this rectangle and that triangle and just add them together? Wouldn't that work out perfectly? Absolutely. It would work out perfectly. But we could also look at these two rectangles. We could take the one endpoint, which has 2 and 4. We could take the other endpoint, which would have 2 and 5. And one we would call a lower sum, and one we would call an upper sum, because one is lower than it should be, and one is larger than it should be. If we take the average of those two, we get 9, which happens to work out perfectly in this case, because if you see the bigger and the smaller together, do you see that that diagonal line would cut it perfectly in half? But we have one that's an underestimate and one that's an overestimate. And if we find the average of those, it actually works out perfectly. But we don't decide to work out perfectly yet. We just make things a little bit smaller. So now if I did 2 rectangles, I could have 2 rectangles that are below and 2 rectangles that are above. And one's going to be too small and one's going to be too big. But before we had 8 and 10. And now, I know you know the answer is 9. But now we have 8 and a half and 9 and a half. We're getting closer. Not rocket science, but do you see that as you increase the number of subintervals or the number of rectangles, then our area improves. Okay, and we know the actual area is 9. Now this one we could find the actual area because it ended up being a straight line which had a triangle, so it wouldn't be problematic. Everybody good? So as you increase the number of rectangles for both the upper and the lower, the estimate gets closer and closer. This Archimedes did as a Greek, he called it his method of exhaustion. Just keep doing it until you're tired, and then you're probably pretty close. And if you want to get closer, just get more tired and keep doing it for long. And if you want to get closer than that, keep doing that for long. Okay? So now, we take A to B, and we break it up into a bunch of little sections. Does it make sense if you decided on n sections, you would take the distance between A and B, which is just B minus A, and divide it by however many sections you want. If you wanted 10 sections, you divide by 10, and they would all be equal size. If you wanted n sections, you would divide it by n, and that would tell you that the amount that you're changing each time is whatever the total distance was, B minus A, divided by how many sections you want. B minus A divided by n. And we get some nice notation stuff happening here. We're going to use some sigma formulas coming up, because we're going to add a bunch of the same thing over and over again. So one of the things we did yesterday, for those that weren't here, is we reviewed sigma notation and what it meant. Okay? So what's going to happen? Well, the area of the first rectangle, this distance here, is always your change in x. That stays constant. That's going to be b minus a over m. And then you pick a value, and you can either pick the left side or the right side. It really doesn't matter. Sometimes they have left side sums, sometimes they have right side sums, sometimes they have upper sums, sometimes they have lower sums. So whichever side you choose, and in this one it says C1, so it choose X1, choosing the right-hand side. Choosing the right-hand side times by that, that'll be the area of that first rectangle. The second rectangle will choose the area of X2 and multiply it by the width, and so on. Actually, in this one, if I look at my rectangles, doesn't it look like it's choosing the left side of the rectangle, not the right side of the rectangle? There we go. So the area of the last one would be whatever our last term is. Oh, I'm looking at my diagram. You see that sometimes it chooses the left point and sometimes it chose the right point for the rectangle. So the diagram is always choosing whichever point made the rectangle smaller. To guarantee, this is called a lower sum. It guarantees that my sum is too small. Probably compare that with the upper sums, which guarantees that the sum is too big. And then you would have bounds where you would say the area would be between. So if we were adding all of these up, we could write this in sigma notation. We always had in each of those rectangles a change in x, because the bottom width was the same every single time. And then we always had this f of c1, that's your height of your rectangle. And that's going to depend on which value you choose. in this example that we had, the f of C1 always chooses the minimum point on that little subinterval. That way we're guaranteed to have our sum to be an underestimate. Does that make sense that if any little tiny bit of your graph, you always took the minimum point in that and made the rectangle with the minimum, you guarantee that your rectangle will be too small. And this would be called the lower sums. Can you see that you could do the exact same process but always choose the maximum point in the interval? And those would be the upper sums. So we have, for the lower sums, they used a little tiny c. And then the upper sums, a big capital C. To be like, oh, that's bigger. Totally intuitive then. Notation-wise, though, we're getting a little complicated. Because we've got this sigma notation. All this sigma notation is saying you're going to have a bunch of different rectangles. Every rectangle has the same form. It always has a change of x and always has a height. For one rectangle, the height is the smaller one. For the other rectangle, the height is the bigger. And the wonderful thing about this is in the end, if you don't completely understand what's going on, you're going to be okay. But it's not too crazy. Okay, so we have one sum with a little s, because it's the underestimate, and one sum with a big S, because it's an overestimate. And what's going to happen is we're going to find out that if we go to infinity, these two sums converge on the same number, and therefore the number that they converge on must be the actual area under that curve. Okay. So we're going to find the area under x squared. Right? That's not something you have a formula for. And we're going to go from 0 to 10, and we're going to use lower sums. So if we did this in two sections, from 0 to 10, does that make sense that each of your sections would be 5 width-wise? Okay? And you're going to add up both of those rectangles using the lower sums. The first rectangle, change of x is constant, right? So it's a constant. You can pull it out with properties of sums in front. So that 5. F of 0 happens to be 0. F of 5 is 25. We have an estimate of 125. On a scale from 1 to terrible, this estimate is probably terrible. All right, look at the actual area under the curve. You can see where 125 is. I don't even think might not even be halfway there. It's a terrible estimate. Usually if you estimate something with two intervals, it's not going to be the greatest. But even though we have a terrible estimate, next, were you not done? I can go back. Sorry, I get excited sometimes. I get excited about what's coming next. So, two subintervals, not a very good. You see, like all the green that's shaded is all error right now. We've got a lot of error. Tell me when you're ready. Ready? Kevin? You good? Okay. So now, we're like, well, what if we did 5 subintervals? Can you see that now the width of each of those rectangles is going to be 2? And your lower sum would again always use the left-hand side here. Change your x, you could bring out in front because it's a constant. We have f of 0 and f of 2 and f of 4 and f of 6 and f of 8. We add those all up. We still have error. We're at 240 now instead of 125. You know, with sports, there's like, during the game you can bet, like they're like advertising it everywhere, all these things you can bet on, like, oh, you're in the middle of the game, you can bet on. Always like, ooh, we're in the, should they have like, I don't know, I'd probably get fired if they had like in-class betting during calculus class. What do you think, right? What's the area under the curve? After the first example, you knew it was going to be bigger than 125. So now you start placing your bets. You got better odds right now. Now, we're at 240. You know that it's going to be bigger than 240. Right? Take our bets. Whoever's the closest gets to choose somebody else in class and steal some of their marks. No. That would be... That'd be terribly mean, eh? It's not like you get bonus marks. No, you choose somebody. Their mark goes down. Your mark goes up. Talk about animosity created in math class. Oh. Okay. Anybody want to guess where they're thinking it's going? What do you think the area under the curve is going to be? It's more than 240. You think it'll get up to 2,000? I don't think so. 300. Okay. We got someone saying 300. Let's do 10 intervals. This is going to be closer. Right? Can you see why they call this a method of exhaustion? Because the first one that was terrible wasn't too much work, but it was a terrible estimate. So we would do the same thing, but now we have a sum of 10 things. So we have to figure f of 0, f of 1, f of 2, f of 3, all the way up to f of 9. Figure it out. We're 285, 300 is still a possibility. Anybody else want to put out their guesses based on the error that's there? How much do you think all that error would add up to? 300 exactly? 300 would be nice, wouldn't it? 333. And the actual answer, that's very close. 333 and a third. If you wanted to get closer to 333 and a third, I would say in your spare time this weekend, do 1,000 intervals. Have fun with that. And add them all up. Sure, you could train AI to do it for you, so you don't have to do all those calculations. Actually, it'd be quite pretty. Sure, it would do that. It's going to get to 333 and a third. So what we're doing is we're developing the idea. Super important, and you will have some questions that involve sums coming up. Will you get mad at me if I show you the shortcut like really quickly? No? we're not even close there yet. But what we're finding here, if area under a curve is related to integrals, and this function is x squared, we're really finding an integral of x squared, but we're not just finding any integral, we're finding a definite integral because we want to go from 0 to 10. So we're going to add these numbers here. And you already know how to work backwards. What is the integral of x squared? Add 1 to the exponent, divide by the exponent, put that in brackets, and I'll put 0 and 10 here. We don't need the plus c when we're doing a definite. And what we're going to find out is that this is, like, we still have a lot of mathematics to go before we find this out. But if you add up all of these rectangles, it is the same as taking the 10 and plugging it in. Then taking the 0 and plugging it in. And subtracting. 10 cubed is 1,000. 1,000 divided by 3 is 333 1/3. And then this is a little bit more complicated, but if you use a calculator, you're going to get this as 0. You get 333 over 1/3. But do you know how many rectangles people added for many, many years before they figured this out? So we've got Archimedes doing the method of exhaustion, and he kept it named that way because he didn't see the connection between calculus and this, because calculus only happened like 1,800 years later. Crazy time frame wise. This is much more straightforward.
I was wondering if you could go back to the last one and explain the subscript, superscript, like the numbers on the last part you just talked about.
The numbers, like the 0 to 10 represented that we wanted to find the area under the curve from 0 until 10. So that's why 0 to 10. Okay. We integrated like normal by adding 1 to the exponent and dividing. I kept my 10 and 0 there because then I plug in the top number and subtract plugging in the bottom number.
Okay.
So that's where I plugged in the 10. 10 cubed divided by 3 is 333 1/3. Plugged in the 0. 0 cubed over 3 is 0. Subtracted them and still ended up with 333 1/3. Mathematically, this is not very much, like that was not very much work. Cheated and showed it to you early. This is one of the benefits of taking calculus in high school before university. Often university professors don't ever want you to see the shortcuts that are coming later. So you know when you know all the derivative rules, you know? They'll spend 2 weeks with the Newton's definition with the limit. And all the students that have never taken calculus ever before are like, oh my goodness, this is the hardest thing, the longest thing I've ever done, and we have to do this over and over again. And you'll be sitting in there like, oh, I know the shortcut. So many of the things that calculus is wonderful for is it creates huge shortcuts. But we have to see, you have to go slug through what happened to get there. And that's, we're in a slugging, next couple of days we're going to slug it out. Okay. Approximate the area under y equals x plus 1 from 0 to 4 using lower sums and upper sums with an interval of width 1. Translated to regular life is, here's a simple problem, but instead take a fork and poke your eyes. Because you could so easily find the actual area. It's a straight line. It has triangles and rectangles. You could so easily find the area. But no, we are going to write out the sum formula for the lower ones and write out the sum formula for the upper ones. Which means we're going to add up 4 rectangles. No, yes, 4 rectangles. The distance is 1 in between each of them from 0 to 4. our change in X is 1 every single time. You can pull that out for the big ones and the small ones. Does it make sense that if I drew a picture, which I've got here, do the whole thing. Got the picture here. Does it make sense when you're doing the lower ones, because the line is increasing, the lower ones would always include the left-hand point of the interval. And the upper ones would always include, here I'll color them in here. I choose the left point, the left point, the left point, the left point of the 4. And then the second one, you're always choosing the right point for your rectangles. This will always be true if something is increasing. So you can imagine they could ask you to do the derivative to show that it's always increasing. Meanwhile, finding that area would be so easy with just one rectangle and one triangle.
Do I have to write out the whatever one the people add and then one after that, or can I just go from first one to last one?
First one to here?
No.
From where to where? You want to go from
From first one and from one to last one.
from here to
Yeah.
here? Yeah. Just showing that you can factor it out. And then we add them all up, we get 10 as the area for the lower one. And the upper ones, sometimes it's nice to actually show them and label them. 2 plus 3 plus 4 plus 5, we get 14 for the upper ones. So we know the answer is somewhere between 10 and 14 from this method, which if you would have done it a lot quicker, you could have figured out the answer was 12 with a lot less work. But we're developing a concept.
Hi, can I get Mateo to the office? He's getting excused right now.
Okay.
Thank you.
You have a match? Or no? No. Oh. Maybe it's the dance. Somebody wants to dance with you and they got you excused. I think that's it. That's very likely. Everybody good? Roar? Awesome. Okay. So this seems like more of a reasonable question to do because I don't know the area under 4 sine x plus 1. There's my picture. All right, have a good weekend. From 0 to 3. So I drew it on my graphing calculator, then I added a bunch of rectangles there. And every single time I made my rectangle so that it was below. See how that works? So I chose, for rectangle number 1, I would have chosen the left-hand point. For rectangle number 2, the left-hand point. For rectangle number 3, the left-hand point. For rectangle number 4, it looks like that was lower than the left-hand side. And then I chose this lower point and that lower point. And that would guarantee that my sum for sure would be less than it should be. I'm going to zoom back in. I'll have that diagram at the bottom later for you, just so that it's a little bit easier to read here. So in inscribed rectangles, inside means it's going to be lower. If I have 6 of them, Well, the distance from 0 to 3 is 3, divided in 6 equal sections. Each one will be a half. So we add them all up. And then you could do a table of values on your calculator for this. Do you know how to do that on your calculator? Quickly? I feel like doing it just because I think it would be fun. Sorry. I'm going to go y equals, I'm going to clear it out, and you're mad because you can't see what you need to write. I will, wow, this is scary. I do, yes. If I do that, can you still see what you need to see? So that means if I do. Oh my goodness, now everything, I'm trying to be, I'm failing miserably here at trying to do something I should know. Oh. I'll just give you some time to write a few things down. I think that might just strategically be better. His bird's right here. Wonderful. Note to self. It really doesn't matter if you copy a few numbers down wrong. You're never going to check it. True, right? If you want to do one less decimal place, just do one decimal place. What we want here is the idea. So when you look at your notes later, you want to see, do you see the idea that's happening? So if you can do the idea with less decimal places, perfectly fine. Ooh, I have a brilliant idea. I freeze the screen. I can play around without covering up what you can't see. Oh. If you miss class and are watching the video, you're still screwed. Oh well, you could have paused it. Now you have to hit the 10-second back button to pause it. You're going to be fine. skipped one. Yes. So let's do a little explanation of the one that skipped. I'll unfreeze it, and then we'll go to some shortcuts on our calculator, how you could get these numbers quickly. By the way, the final answer, 9.21. I'm going to view the whole page here so we can see everything. I'm going to put this on. So now, when deciding for the rectangles, we wanted to choose the smaller value. When I looked at rectangle number 1, can you see that the left point is smaller? When I look at 0 and a half plugging in, can you see that 1 is less than 2.9? That's why we decided on using this one for the first one, for C1 is 0. Then between a half and 1, this one's lower. Then between 1 and 1 and a half, this one's lower. But between 1.5 and 2, now 2 became lower than the 1.5. So to make it inscribed, to make it the smaller ones, now we start choosing the right-handed ones. So it's like in every interval, we chose the smaller one of the two. Does that make sense? Of why there's that skip in between. Now, if you go to your graphing calculator, and you type in 4 sine x plus 1, you could graph it, and I changed my window to see a graph. Okay, that's nice. But if you hit second graph, you get a table of values. What's nice about the table of values is it gave me 0, 1, 2, and 3, but I wanted the halves. Now there's a long way to change it to a half, and there's a quick way to change it to a half. The quickest way to change it to a half is just like, no, that wasn't it. Trying to remember the quick way to change it to a half, and what I thought didn't work. Maybe no, it's not. I'm pretty sure it works on my calculator, but let me just I remembered a button. Sometimes you need to hold the actual calculator you normally do something with in order for it to work. You hit the plus key, and then you can change your table. I'm going to change it to a half, and now push enter, and now it changes my value. As soon as I picked up my calculator, my finger went to the right button. Same thing happens to me every year with my photocopy code. I'm like, someone asks me, what's your photocopy code? I'm like, I have no idea. And then I just walk up to the machine and I go, fingers, do your magic, and they just, oh. And they know what to do, and I get into the photocopier. But if I had to tell someone my photocopy code in September, it's gone. So I had to hold the calculator. Then I remember the plus key lets you change it to any value you want. Right? Sometimes if I wanted to look at the numbers in the hundreds, I sometimes go plus 100, then I go to the 100, and then I go plus 1. And now I've got all my numbers in the hundreds. But I don't want to be there. So I'll go back to 0. Plus 0.5. These little tricks can save you some time. So now we could have gotten all of these values, right? Another really handy thing. Another really handy thing you can do is take your finger and grab your computer screen and just put it on your notes, and then you have them. I'm sure that works with your calculator as well. So that's how we could get that table of values quickly. Is this a good method? No. We're going to find a much better method, a much quicker method, a much more accurate method. We're going to find out ways that we can actually use our calculator. Let's see. Oh, I feel like, again, the buttons are, I think it's under the draw. Second draw? No. second calculate. I want to do 0. Yes. 3. It just shaded it all in there for me. And what did we get? We had 9.2. The actual answer is going to be 10.9599997. Your calculator has ways to figure that out. So what did I do? I went second, let's add that graph, and I went to calculate, where second calculate lets you do all the calculations you want with a graph. And notice, they have the integral at the bottom, and if the integral finds the area under the curve, now you can just go from 0 to 3, boom, it shades it in for you and finds you the actual answer right away. Again, we're not supposed to know that yet, so we still have more tedious math to go before we get to all the shortcuts. All right, let us see if we can get the last question done. Nice end of the notes if we do. So to find the actual area, we'd have to do an infinite amount of rectangles, which involves us using a limit. If we have all of the lower sums, and we do the limit as n, which is the number of intervals that we have, goes to infinity, and take all of the upper sums and did it to infinity, they would end up being the same number, and that would be the actual area. I'll make this wide again. So now we're going to see if we can do that limit for something that you could just easily find the area for anyways. Right? 3x, is this my graph? No, my graph is nice. So does it make sense that if you had n subdivisions, then you would take your width of 10 and divide it by n parts? And we'd have our lower sums and upper sums. Things get a little bit abstract here, but it's not, if you take a little step at a time, it's not too bad. Have a picture? Not really. Okay. I'll draw like a mini picture here for you that I think can be helpful. And we're going to zoom in to one section. Let's say this is really zoomed in, because I have an infinite amount of sections, there's a ton of them, but if I really, really zoomed in, there would be a space between them. And this width here is 10 divided by n, however many spaces I have. Then that rectangle would go up, hit my curve there, and hit my curve there, creating a possibility for a lower sum using that rectangle and upper sum using the one on the bigger part. But let's just look at the lower one for now. If I wanted to use the lower sum, then my endpoint would be this one. So in this list of endpoints, you see that you're always choosing the left-hand side because it's increasing for the lower sums. So we start at 0. And then the very first one will be whatever 10 over n is, because that's the space. And the second one would have 2 of those spaces. The ith one would have I of those 10 over n spaces. And finally, you would get to the nth one, which would have n of those spaces, right? And that would just equal at 10 if you went to infinity. Even though it's the left-hand side, I know, we're crazy that way, but if it's so big to infinity that they're so small, you're basically at 10 when you would have infinite amount. Okay. So that's the idea. With that, that means that we're looking at a pattern here, and the pattern is that you would always have 3, right? Well, we've got our change in x, we've got c of I being 10I over n, this is the general one, and since our formula is, our equation is 3x, that's why we would have 3 of these, which would be 3 of those. Okay, so we've got our pattern formula set up. And yes, this is one we could easily calculate the area just using our triangle formula. But let's make sure we don't keep that in perspective because we're doing something really painful instead. So we get this equation where each xi is really 10I over n. So I can replace the xi with 10I over n. We're going from I equals 1 to n. Simplifying the math that we have, because we've got 10 times 10 times 3, that's going to be 300. The n on the bottom is going to be an n squared, and we have an I. The 300 over n squared is a number. Assuming n is some number you went up to, 300 over n squared is a number. You can bring that out in front. And we end up with, beautifully, I equals 1 to n of just I. Why is this so beautiful? Because it's one of the formulas that you learned in arithmetic sequences and series, adding up the first n amount of numbers. That was one of the formulas that was listed the other day. It's just n times n plus 1 divided by 2. Which the 300 and the 2 simplify to 150. One of the n's cancels out. We have n plus 1 over n, which we could unadd fractions. And write n plus 1 over n is really 1 plus 1 over n. Right? If you divided the n by n, you'd get 1. If you divided by 1 by n, you'd still have 1 over n. And so our sum, our lower sums, are 150 times 1 plus 1 over n. This is the formula for any n. It's kind of nice. So if you decided to just do 2 partitions, you'd have 1 plus 1 half. If you did 10 partitions, you'd have 1 plus 1 tenth. And if we take the limit as n goes to infinity, the 1 over n would be 0. Because of this 300 and this 2.
Oh, okay, yeah.
Yeah. No, it's fine. Sometimes, sometimes the things you like think they're magical, but then you're like, oh, yeah, that makes sense. But until you see it, it seems like it's like, what the heck happened?
Yeah.
But if you happen to have a triangle with a base of 10 and a height of 30, I would probably recommend this new technique for finding the area. I definitely wouldn't go base times height divided by 2 and get 150. Higher level learning is about pain and suffering. We're now going to do things in the most difficult way we can think of for the rest of our life. But because someone decided to look into this most difficult way of thinking, we developed the fundamental theorem of calculus and we come up with the most simple way of finding areas under any curves, which is really miraculous. But for this example, this is terrible, right? Agreed? So you might have to take some time to like digest. I find it's really difficult in your head to hold like thousands of little rectangles and imagine them all individually, but generally all at the same time. Your brain gets like, which rectangle were you thinking about? Gets very confused. Okay? So if you break it down, it's actually not that bad. The key things here, we want to take out my highlighter. We want to find out what the general I1 looks like. And then use that to create your equation. Have a wonderful weekend.